Hello, my name is Kendall Lamb and this is Lab 4, Oscillations. So the purpose of this lab was to compare an experimental model with a computational model of a spring oscillating in two dimensions. We also plotted the changes in kinetic and potential energy over time, as well as the changes in total energy. And here is a quick preview of how the two models ended up matching up. So for the main physics concepts, the first one is the momentum principle. Net force equals change in momentum over change in time. And this was an important principle in modeling our object's motion in GlowScript by looking at what forces were acting on the object and then using that along with these two equations, velocity update and position update, to continually model the object's motion. Um, so for forces, there's two forces acting on our object in this lab. First is the force of the spring. We can see that is proportional to the spring constant K, as well as the amount that the spring is compressed or stretched, which is that S value. Another force is the force of gravity, which is magnitude mg in the negative y hat direction, close to Earth's surface, that is. Another important concept is the energy principle. Change in energy equals work done on the system. And here we also have the formulas for kinetic, U-grav, and U-spring energies. So for initial conditions and constants, the system I chose was the spring, the earth, and the ball. No surroundings, meaning no work was done on the system. So this was the initial position from tracker of the weight from the spring. The initial velocity was 0 because I assumed that it was dropped from rest, and the initial spring setup was that it was the L vector is the same as the ball position, and the rest length as well as the spring constant were given to us before. So now let's take a look at the tracker video. You can see here that the weight here is being tracked by this red dot right here, and the position X and Y are being graphed on these graphs over here. And the data from here was taken and put into a CSV file so that we could put that into GlowScript to compare it to the computational model later. Alright, now we're here in GlowScript looking at the code. First thing is we get the initial conditions of the ball, set up the mass, position, and the velocity. Then we get the CSV data so we can compare the experimental and computational models. Right here we set up the initial setup for the spring, the L vector, rest length, the spring constant, all that stuff. Then we calculate the initial energies. So we go down here into the iteration loop. We can see that we first set the initial energies to the energies from the last update. And then we calculate the net force, the force from gravity, the force of the spring, and then we update velocity and position using the formulas for those. We update the spring based on the new ball's position, and then we go ahead and calculate the new energies as well as the change in energy, and then we can go ahead and plot everything. So now if we run the program and we put our CSV in, we can see that the model looks pretty similar between the computational and experimental models. It follows pretty closely. And right here we can see change in energy is 0 as expected because no work's being done on the system. Going down we can see that comparing the models, the experimental model gets further and further away over time, which is probably due to drag. In the y direction there's a little bit of difference in the amplitudes, but it's still pretty similar. Alright, so for sources of error, first we assume that the initial velocity is 0 when the weight was released. Second, we didn't account for air resistance and the force of drag. So third, the realized spring was not ideal. We assumed that the spring was massless and that it would perfectly follow Hooke's law when in real life the spring isn't ideal. And lastly, the camera perspective could have messed up the tracking. For what does it mean? Is the energy principle satisfied? Yes, it is satisfied because we define the system to be the spring, the earth, and the ball for this lab, and that means that there's no external work being done on the system, and so the change in energy should remain 0 throughout, which it does. And lastly, looking at the periods in the x direction and the y direction, by looking at these cycles right here on the graphs, and finding the average time it takes to complete one cycle for both the x and the y direction, we can go ahead and find the average period for an oscillation, which we calculate to be 1.638 for x and 1.520 for the y position. This is about a difference of 0.1 seconds, so it's not much. But looking at this formula right here, if we were to calculate the spring constant from the period, we would get different answers. Thank you for listening.